Take any piece of matter anywhere in the observable universe and break it down far enough, and you will eventually arrive at a small set of fundamental particles governed by a small set of fundamental forces. The electron sitting in its orbital around a nucleus, the quarks packed inside a proton, the photon carrying light across a room, the force holding atomic nuclei together against the electrical repulsion of their protons. All of it is described by a single theoretical framework called the Standard Model of Particle Physics. That framework was assembled across several decades of the 20th century, refined through thousands of experiments, and tested against reality with a precision that no other scientific theory has matched. The precision is worth sitting with for a moment, because it is what makes the Standard Model's limitations so significant. The magnetic moment of the electron, a measure of how strongly the electron responds to a magnetic field, has been calculated using the Standard Model and measured experimentally. The agreement between the two is accurate to better than 1 part in a trillion. That is the equivalent of measuring the distance from one side of a continent to the other and being correct to within the width of a human hair. No other prediction in the history of science has been confirmed to this level of accuracy, and the Standard Model produces it routinely for quantity after quantity across decades of increasingly precise experiments. The framework describes 12 fundamental matter particles, 6 quarks and 6 leptons, organized into 3 generations of increasing mass. It describes 4 fundamental forces: electromagnetism, the weak nuclear force, the strong nuclear force, and the interactions between them, each mediated by a specific set of force-carrying particles. It describes how these particles acquire mass through their interaction with the Higgs field, whose associated particle, the Higgs boson, was detected experimentally in 2012 after a decades-long search. Every particle the Standard Model predicts has been found. Every interaction it describes has been confirmed. Every precision test it has been subjected to has returned results consistent with its predictions. This is a framework of extraordinary power and reach. It accounts for the structure of atoms, the behavior of light, the fusion processes inside stars, the radioactive decay of unstable nuclei, and the behavior of matter at the highest energies ever produced in a laboratory. It is not an approximation or a model in the loose sense of a simplified description. It is a precise mathematical theory that has been tested in every accessible regime and found correct in every case. And yet, it is the tip of the iceberg. Everything the Standard Model describes with such extraordinary precision accounts for roughly 5% of the total energy content of the observable universe. The remaining 95%, the dark matter, the dark energy, the gravitational force governing the large-scale structure of everything, is outside the framework entirely. The theory that predicts the electron's magnetic moment to 1 part in a trillion has nothing to say about the majority of what exists. That gap is not a minor technical issue awaiting a small patch. It is a sign that the Standard Model, for all its precision, is describing a surface, and beneath that surface lies a structure whose depth and character the Standard Model gives almost no guidance toward. What the chain ahead maps is how that structure becomes visible, gap by gap, through every place the Standard Model reaches its edge and stops. Before we continue, I'd like to invite you to like this video if you enjoy exploring topics like these, and to consider subscribing for more. Share your thoughts in the comments below, and feel free to suggest future topics you'd like us to explore. With that said, let's get back to the topic. The first and most fundamental gap is not about dark matter or dark energy. It is about the force that governs the large-scale structure of everything, the force felt by every massive object in the universe, the force that was the first to be described mathematically and remains the last to be incorporated into a quantum framework. The Standard Model describes 3 of the 4 known fundamental forces with extraordinary precision: electromagnetism, the weak nuclear force, and the strong nuclear force are all incorporated into the framework as quantum field theories, each with its own set of force-carrying particles and its own mathematical structure. The framework handles them consistently, allows them to be calculated to arbitrary precision, and produces predictions that match experiment at every scale that has been tested. 3 forces unified within a single coherent quantum mechanical framework. Gravity is absent, not approximately described, not handled with some loss of precision, but entirely outside the framework. The Standard Model contains no graviton, no quantum field theory of gravitational interaction, no mechanism for incorporating the curvature of space-time into its mathematical structure. Gravity is handled separately by general relativity, which describes it as the geometric curvature of space-time produced by the presence of mass and energy. General relativity is itself an extraordinarily successful theory, confirmed by the bending of light around massive objects, the precise timing corrections required by GPS satellites, the detection of gravitational waves from merging black holes, and the large-scale structure of the universe. But it is a classical theory, not a quantum one, and it is completely separate from the Standard Model. This separation is not merely an aesthetic problem of theoretical unity. It is a practical failure with specific physical consequences. At the scales where both quantum mechanics and gravity are simultaneously important, inside black holes, at the moment of the Big Bang, and at the Planck scale where quantum fluctuations of spacetime become significant, neither the Standard Model nor general relativity can be applied reliably. The Standard Model ignores gravity entirely, treating spacetime as a fixed flat background rather than a dynamic entity. General relativity ignores quantum mechanics, treating matter as a smooth, continuous distribution rather than a collection of discrete quantum fields. When both matter and gravity are simultaneously in a regime where quantum effects are essential, both theories break down and neither provides a valid description. The attempts to construct a quantum theory of gravity have occupied theoretical physicists for decades without producing a confirmed framework. String theory is the most developed candidate, postulating that particles are not point-like objects, but tiny vibrating strings whose different vibrational modes correspond to different particles, with gravity emerging naturally from one particular vibrational mode. Loop quantum gravity takes a different approach, quantizing space-time itself into discrete chunks rather than treating it as a continuous background. Both frameworks have produced significant mathematical insights, but neither has made predictions that can currently be tested experimentally, and neither has achieved the status of a confirmed physical theory. The absence of gravity from the Standard Model means that the framework is fundamentally incomplete as a description of physics, independent of every other gap in the chain ahead. A theory of everything must account for all 4 forces. The Standard Model accounts for 3. The missing force is not a minor one. It is the force that determines the large-scale structure of the universe, governs the formation of galaxies and stars, controls the fate of massive objects collapsing under their own weight, and shaped the earliest moments of cosmic history. Its absence from the quantum framework is not a gap at the edge of the Standard Model. It is a gap at its foundation. The Standard Model describes the particles that make up ordinary matter, the electrons, quarks, neutrinos, and force carriers that constitute everything that has ever been directly detected in a laboratory. Ordinary matter is the matter that emits light, absorbs light, interacts electromagnetically, and responds to the full suite of forces the Standard Model describes. It is the matter that stars are made of, that planets condense from, that living organisms are built out of, and it accounts for approximately 5% of the total energy content of the universe. The remaining 27% of the universe's energy content is dark matter, a form of matter that does not emit, absorb, or scatter light in any detectable way, does not interact through electromagnetism, and has never been directly detected in any laboratory experiment, despite decades of increasingly sensitive searches. Its existence is inferred from its gravitational effects, which are unambiguous and pervasive. Galaxies rotate at speeds that cannot be explained by the gravitational pull of their visible matter alone. The outer edges of galaxies move as fast as their inner regions, a pattern that requires a large halo of additional mass surrounding each galaxy to provide the extra gravitational pull. Galaxy clusters bend light from objects behind them far more strongly than the visible matter they contain can account for, an effect called gravitational lensing that maps the distribution of mass regardless of whether that mass emits light. The large-scale structure of the universe, the web of filaments and voids that galaxies are distributed along, matches the predictions of cosmological models only when a large component of non-luminous matter is included. Every one of these observations points to the same conclusion. There is more matter in the universe than the Standard Model's particles can account for, and that additional matter interacts gravitationally but not electromagnetically. It is present in every galaxy cluster, and woven through the large-scale structure of the cosmos. It outweighs ordinary matter by a factor of roughly 5-to-1. The Standard Model has no particle that fits this description. Every particle in the framework either interacts electromagnetically, making it detectable by light-based instruments, or is so light and weakly interacting that it cannot account for the observed gravitational effects. Neutrinos, the most weakly interacting Standard Model particles, were once considered candidates, but their masses are too small and their velocities too high to produce the clumped distribution that dark matter observations require. The framework simply does not contain anything that behaves the way dark matter behaves. Numerous extensions to the Standard Model have been proposed to fill this gap. Weakly interacting massive particles called WIMPs were for decades the leading candidate, predicted by supersymmetric extensions of the Standard Model and expected to be detectable in underground experiments sensitive to rare particle collisions. Decades of searches have found nothing. Axions, ultralight particles originally proposed to solve a different problem in the Standard Model, are another candidate currently being searched for with dedicated experiments. Sterile neutrinos, primordial black holes, and entirely new dark sector forces have all been proposed. None has been confirmed. Dark matter remains the dominant component of the universe's matter content, and the Standard Model's most glaring omission from the description of what matter actually is. Dark matter is the larger of two invisible components that the Standard Model cannot account for. The second is darker in a different sense. Dark matter at least behaves like matter, clustering gravitationally, forming halos around galaxies, participating in the gravitational dynamics of the universe in ways that can be mapped and characterized. Dark energy does none of these things. It does not cluster. It does not respond to gravity in the way matter does. It is distributed uniformly across space, does not dilute as the universe expands, and its only observable effect is that it is pushing the universe apart at an accelerating rate. The acceleration of the universe's expansion was discovered in 1998 through observations of distant supernovae. Type 1a supernovae are used as standard candles, objects whose intrinsic brightness is known well enough that their distance can be inferred from how bright they appear. Observations of supernovae at large distances showed that they were dimmer than expected, meaning they were farther away than the expansion rate of the universe at that time would have placed them. The universe was not just expanding, it was expanding faster than it used to, driven by something that was pushing space apart against the gravitational attraction of all the matter within it. That something is dark energy, and it accounts for roughly 68% of the total energy content of the universe. It is by far the dominant component of cosmic energy, outweighing both ordinary matter and dark matter, combined by a large margin. And the Standard Model has nothing to say about it. The framework describes particles and their interactions in a fixed or slowly varying space-time background. It has no mechanism for a form of energy that is intrinsic to space itself, that does not dilute as space expands, and that drives the accelerating separation of everything in the universe from everything else. The closest the Standard Model comes to addressing dark energy is through the concept of vacuum energy. Quantum field theory predicts that empty space is not truly empty. It is filled with quantum fluctuations, virtual particles appearing and disappearing on timescales, consistent with the uncertainty principle, contributing a baseline energy density to the vacuum itself. This vacuum energy has the right qualitative properties to act as dark energy. It is intrinsic to space, does not dilute with expansion, and would produce a repulsive effect on the large-scale structure of the universe. But the quantitative prediction is catastrophically wrong. When the vacuum energy contributions of all the quantum fields in the Standard Model are calculated and compared to the observed value of dark energy, the discrepancy is enormous. The calculated vacuum energy exceeds the observed dark energy density by somewhere between 50 and 120 orders of magnitude, depending on the energy scale at which the calculation is cut off. This is the largest discrepancy between a theoretical prediction and an experimental observation in the history of physics, by an enormous margin. The Standard Model not only fails to explain dark energy, its most natural prediction for the quantity that should correspond to dark energy is wrong by a factor so large it has no analogue in any other domain of science. Something is cancelling the vacuum energy contributions almost perfectly, leaving a tiny residual that drives the observed acceleration. What that cancellation mechanism is, and why it leaves precisely the small residual that is observed, is completely outside the Standard Model's explanatory reach. Dark energy is not just an omission from the framework. It is a signal that something fundamental about the relationship between quantum field theory and the large-scale structure of space-time is not understood. Every particle in the Standard Model has a corresponding antiparticle with identical mass and opposite charge. The electron has the positron, the quark has the antiquark, the proton has the antiproton. When a particle and its antiparticle meet, they annihilate, converting their combined mass into energy in the form of photons. This symmetry between matter and antimatter is built into the mathematical structure of the Standard Model at a deep level, following from the combination of charge conjugation, parity transformation, and time reversal that the theory preserves in its fundamental interactions. The symmetry creates an immediate problem when applied to the early universe. If matter and antimatter are produced in equal quantities and if the laws of physics treat them symmetrically, then the Big Bang should have produced equal amounts of both. As the universe cooled and the energy density dropped, matter and antimatter should have found each other, annihilated completely, and left a universe filled with nothing but photons and no matter at all. No galaxies, no stars, no planets, no atoms of any kind. A universe of pure radiation expanding into emptiness. The universe that exists is not that. It is filled with matter, structured into galaxies and stars and planets and everything that inhabits them, with essentially no primordial antimatter to be found anywhere in the observable volume. The antimatter is gone. The matter survived. Something in the early universe broke the symmetry between them, producing a slight excess of matter over antimatter, and that excess, after the annihilation of equal quantities of each, left the matter that now constitutes everything observable. The excess was small, roughly 1 extra matter particle for every billion matter-antimatter pairs, but it was enough to produce the entire material content of the observable universe. The Standard Model contains a mechanism for breaking the symmetry between matter and antimatter, called CP violation, where CP refers to the combined symmetry of charge conjugation and parity transformation. CP violation has been observed experimentally in the decays of certain particles, confirming that the Standard Model does allow a small asymmetry between matter and antimatter processes. But the amount of CP violation the Standard Model permits is far too small to account for the observed matter-antimatter asymmetry of the universe. The mechanism exists in the framework, but its magnitude falls short of what the universe requires by many orders of magnitude. This means that the matter composing every star, every planet, and every living organism exists because of a process that the Standard Model cannot fully explain. The asymmetry that made the material universe possible required a degree of CP violation that the framework does not contain. Something beyond the Standard Model broke the symmetry between matter and antimatter in the early universe with sufficient strength to produce the observed excess, and that something has left no confirmed trace in any experiment performed since. The universe's very existence as a material structure is a consequence of physics that the Standard Model cannot account for, which makes the matter-antimatter asymmetry not just a gap in the framework, but a gap in the explanation of why anything material exists at all. Neutrinos occupy a peculiar position in the Standard Model. They are among the most abundant particles in the universe, produced in enormous quantities by nuclear reactions in stars, by radioactive decay, and by the processes that occurred in the early universe. Roughly 100 trillion neutrinos pass through every human body every second, arriving from the Sun and from cosmic sources, and virtually none of them interact with anything. They pass through the Earth as though it were not there, interacting so weakly that detecting even a small fraction requires massive underground detectors filled with thousands of tons of material, shielded from every other form of radiation, waiting for the rare collision that produces a detectable signal. In the original formulation of the Standard Model, neutrinos were massless. This was not an oversight or a placeholder assumption awaiting better data. It was a structural feature of the framework. The mathematics of the Standard Model incorporates neutrinos in a way that requires them to be massless, traveling at the speed of light and existing only in a left-handed helicity state, meaning their spin is always aligned opposite to their direction of motion. A massless neutrino cannot have a right-handed helicity state, because for a massless particle traveling at the speed of light, there is no reference frame in which it appears to move in the opposite direction, and therefore no frame in which its helicity appears reversed. Experimental observations have shown that neutrinos have mass. The evidence comes from a phenomenon called neutrino oscillation, in which neutrinos change their identity as they travel, converting between the three known types: electron neutrinos, muon neutrinos, and tau neutrinos, over distances that depend on their energies and the differences between their masses. Oscillation is only possible if the neutrino mass states are different from the neutrino flavor states, and different mass states can only exist if at least some of the masses are non-zero. Solar neutrino experiments, atmospheric neutrino detectors, and reactor neutrino measurements have all confirmed oscillation, establishing beyond any reasonable doubt that neutrinos have mass. Neutrino mass is incompatible with the Standard Model as originally constructed. Incorporating it requires extending the framework in ways that introduce new choices and new questions. The simplest extension adds right-handed neutrino states to the theory, allowing neutrinos to acquire mass through the same Higgs mechanism that gives other particles their masses. But right-handed neutrinos, if they exist, have never been detected and interact so weakly that their detection may be permanently beyond reach. An alternative mechanism, called the seesaw mechanism, generates small neutrino masses by introducing very heavy right-handed neutrinos whose mass scale is far beyond anything accessible to current or foreseeable accelerators. Either way, the Standard Model requires modification to accommodate a fact that has been experimentally confirmed. The framework that predicts the electron's magnetic moment to 1 part in a trillion cannot account for the mass of the most abundant massive particle in the universe without being extended beyond its original structure. And the extension required points toward new physics at energy scales that have not been directly explored, with new particles and new mechanisms that the Standard Model itself gives no guidance toward. Neutrino mass is not a gap at the edge of the framework. It is a confirmed experimental result that the framework in its original form cannot contain. The Standard Model contains a particle whose mass sits at a value that the framework itself has no explanation for and no mechanism to protect. That particle is the Higgs boson, and the problem its mass creates is called the hierarchy problem. It is not an experimental discrepancy between prediction and observation. It is a theoretical instability within the framework itself, a sign that the Standard Model is an effective description operating at accessible energy scales, but resting on a foundation that requires something else to stabilize it. The Higgs boson was detected at a mass of approximately 125 times the proton mass. That value sits at the electroweak scale, the energy scale at which the weak nuclear force and electromagnetism are unified within the Standard Model. The electroweak scale is roughly 100 billion electron volts, and the Higgs mass sits comfortably within it. At first glance, a particle having a mass consistent with the energy scale of the physics it is associated with seems entirely natural. The problem arises when quantum corrections to the Higgs mass are calculated. In quantum field theory, every particle's physical mass receives contributions from quantum fluctuations, virtual particles appearing and disappearing in the vacuum and interacting with the particle in question. For most particles, these quantum corrections are proportional to the particle's own mass, making them manageable and leaving the mass stable against large corrections. The Higgs boson is different. Because of its specific role in the Standard Model, the quantum corrections to its mass are proportional not to the Higgs mass itself, but to the square of whatever energy scale represents the boundary of the Standard Model's validity. If the standard model is valid all the way up to the Planck scale, the energy scale at which quantum gravity becomes important, and which sits roughly 16 orders of magnitude above the electroweak scale, then the quantum corrections to the Higgs mass are roughly the square of the Planck scale. That is an enormous number, many orders of magnitude larger than the observed Higgs mass. For the physical Higgs mass to sit at its observed value, despite these enormous corrections, the bare mass of the Higgs, the mass parameter in the theory before corrections are applied, must cancel against the quantum corrections to extraordinary precision. The cancellation must be accurate to roughly 34 decimal places to produce the observed Higgs mass from the enormous underlying values. This level of cancellation is called fine-tuning, and it is deeply unsatisfying as a physical explanation. It is not impossible in a mathematical sense. The cancellation could simply be a feature of the universe, a coincidence built into the parameters of the standard model at the Planck scale. But it requires the bare mass and the quantum corrections to be independently enormous numbers that cancel almost perfectly, with no mechanism explaining why they should do so. The hierarchy problem is the question of why the Higgs mass is so much smaller than the Planck scale, and why the quantum corrections that should drive it toward the Planck scale are instead cancelled to such extraordinary precision. The problem signals that the standard model is not a complete theory valid at all energy scales. Something must exist between the electroweak scale and the Planck scale that stabilizes the Higgs mass, that provides a physical mechanism for the cancellation rather than requiring it to be an unexplained coincidence. Identifying that stabilizing mechanism is one of the primary motivations for the extensions to the standard model that have been developed over the past several decades, and the failure to find experimental evidence for those extensions at the Large Hadron Collider has made the hierarchy problem more acute rather than less. The hierarchy problem is one instance of a broader pattern running through the standard model. The framework contains numerical parameters, masses, coupling strengths, and mixing angles that must take very specific values for the universe to have the properties it has. Some of those values sit at positions that appear extraordinarily unlikely from the perspective of the theory itself, requiring numbers that could in principle take any value across an enormous range, to instead sit at precisely the value needed for matter, stars, and complexity to exist. This pattern is called fine-tuning, and its presence throughout the standard model is a sign that the framework is missing an explanation for why its parameters have the values they do. The cosmological constant is the most extreme example. As established in the dark energy segment, the vacuum energy predicted by quantum field theory exceeds the observed dark energy density by up to 120 orders of magnitude. For the observed value to emerge from the underlying theory, the vacuum energy contributions of all the quantum fields must cancel against the cosmological constant in the theory to an accuracy of 120 decimal places, leaving a tiny residual that drives the observed cosmic acceleration. No known mechanism produces this cancellation. It is simply a requirement imposed by observation, with no theoretical explanation for why the parameters conspire to cancel so precisely. The strong nuclear force has its own fine-tuning problem, called the strong CP problem, which the next segment addresses in detail. The masses of the quarks sit at values that are small compared to the natural energy scales of the strong force, with no explanation for why they should be so small. The ratio of the electromagnetic force strength to the gravitational force strength is an enormous number, roughly 10 to the power of 36, with no theoretical explanation for why two fundamental forces should differ in strength by such an extreme factor. each of these numerical coincidences could be dismissed individually as an unexplained feature of the universe. Together they form a pattern suggesting that the Standard Model is an effective description whose parameters are set by a deeper theory, and that the fine-tuning reflects relationships in that deeper theory that the Standard Model cannot see. The anthropic argument offers one response to fine-tuning. If the parameters of the Standard Model took different values, the universe would not contain the complexity needed for observers to exist and notice the parameters. Perhaps the parameters are fine-tuned, because only in a universe with these values do observers arise to measure them. This argument has a logical structure and cannot be dismissed entirely, but it is not a physical explanation. It does not identify a mechanism that sets the parameters. It does not predict the values or explain why they sit where they do. It reframes the question without answering it, and most physicists regard it as a last resort, rather than a satisfying resolution. The fine-tuning crisis points in the same direction as every other gap in this chain. The Standard Model's parameters are inputs, numbers that must be measured and inserted into the framework, rather than derived from it. A complete theory of physics would explain where those numbers come from, why they take the values they do, and what deeper structure determines them. The Standard Model offers no such explanation. Its parameters are whatever the universe requires them to be, and the framework has nothing to say about why the universe requires them to be that. The strong nuclear force described by the sector of the Standard Model called quantum chromodynamics governs the interactions between quarks and the gluons that carry the strong force between them. It is the most powerful of the known forces at short ranges, responsible for binding quarks into protons and neutrons, and binding protons and neutrons into atomic nuclei against the enormous electrical repulsion between the protons. Quantum chromodynamics is a precisely tested and extraordinarily successful theory, confirmed by decades of experiments at particle accelerators and consistent with everything that has been measured about the behavior of strongly interacting matter. Within the mathematical structure of quantum chromodynamics, there is a term that can appear in the equations governing the strong force. It is called the theta term, named after the parameter that controls its magnitude. The theta term, if present with a non-zero value, would cause the strong force to violate the combined symmetry of charge conjugation and parity transformation, the same CP symmetry whose violation in the weak force is relevant to the matter-antimatter asymmetry discussed earlier. A non-zero theta term would make the strong force behave differently for matter and antimatter in a specific and measurable way, producing an electric dipole moment for the neutron, a slight separation of positive and negative charge within the neutron that would be detectable in precision experiments. The neutron electric dipole moment has been measured with extraordinary precision. The result is consistent with zero, meaning no detectable CP violation in the strong force has been found. The experimental upper limit on the neutron electric dipole moment places a correspondingly tight upper limit on the theta parameter. The theta parameter must be smaller than roughly 10 to the power of negative 10, meaning it is either exactly zero or so close to zero that no experiment has been able to distinguish it from zero. This is the strong CP problem. The theta parameter is a free parameter of quantum chromodynamics that can in principle take any value between 0 and 2 pi. There is no symmetry in the Standard Model that requires it to be 0. There is no known mechanism that drives it towards 0. And yet it sits at a value so close to 0 that decades of precision measurement have found no deviation from it. A parameter that could be anything is instead essentially nothing, with no explanation for why. The most developed solution to the strong CP problem was proposed by Roberto Peccei and Helen Quinn in 1977. They introduced a new symmetry into the theory that dynamically drives the theta parameter to zero, with the breaking of that symmetry producing a new particle called the axion. The axion has never been detected, but it remains one of the leading candidates for dark matter, connecting two separate gaps in the Standard Model through a single proposed extension. Dedicated experiments are currently searching for axions across a range of possible masses and interaction strengths, with no confirmed detection yet. The strong CP problem is particularly revealing as a symptom of the Standard Model's incompleteness, because it involves a parameter that is not measured to be large and explained, but measured to be essentially zero and unexplained. The framework contains a quantity that should naturally be of order 1, meaning somewhere in the range of values that requires no special explanation, and finds it instead at a value so small that its smallness demands a reason. That reason does not exist within the Standard Model, and finding it requires either a new symmetry, a new particle, or a new understanding of why the strong force respects CP symmetry to a precision that the framework itself does not guarantee. Every gap identified so far, gravity's absence, dark matter, dark energy, the matter-antimatter asymmetry, neutrino masses, the hierarchy problem, fine-tuning, the strong CP problem, points toward physics beyond the Standard Model, at energy scales above those currently accessible. But there is one scale at which the incompleteness of the framework is not a matter of missing particles or unexplained parameters. It is a matter of the mathematical machinery of the theory breaking down entirely and producing results that are not just wrong but meaningless. That scale is the Planck scale, and what breaks down there is the assumption that space-time can be treated as a smooth, continuous background on which quantum fields propagate. The Planck scale is the energy at which the quantum mechanical description of matter and the geometric description of space-time can no longer be treated independently. It is reached when a particle is confined to a region small enough that the energy required for that confinement, through the uncertainty principle, is large enough to curve space-time significantly in the region of confinement. At that point, the geometry of space-time and the quantum state of the matter within it are mutually dependent in a way that neither quantum field theory nor general relativity can handle alone. Quantum field theory assumes a fixed space-time background. General relativity assumes classical matter distributions. Neither assumption holds at the Planck scale, and applying either theory in that regime produces infinities and inconsistencies that cannot be removed by the standard mathematical techniques that work at lower energies. The Standard Model is a quantum field theory, and like all quantum field theories, it is formulated on a fixed space-time background. Its calculations assume that space-time is a smooth, flat, or slowly curving arena in which particles move and interact, unaffected by the quantum fluctuations of the fields propagating through it. This assumption is valid at all energy scales that have been experimentally tested, because at those scales the energy densities involved are far too small to produce significant space-time curvature on quantum mechanical length scales. But it is an assumption, not a fundamental feature of reality, and at the Planck scale it fails catastrophically. The failure is not merely technical, it signals that the Standard Model, as a quantum field theory on a fixed background, is an approximation valid below a certain energy scale rather than a fundamental description of nature. A truly fundamental theory would not treat space-time as a fixed background. It would describe space-time and matter as parts of a single unified quantum system, with the geometry of space-time emerging from the quantum state of the system rather than being assumed from the outset. The Standard Model cannot do this. It is built on top of space-time rather than explaining it, and at the energy scale where space-time itself becomes a quantum mechanical object, the framework has nothing to say. This places a hard upper boundary on the Standard Model's domain of validity. Below the Planck scale, the framework is extraordinarily successful. At the Planck scale, it fails, and the physics at that scale, the quantum behavior of space-time itself, the origin of the space-time geometry that the Standard Model takes as given, and the unification of gravity with the other three forces in a single quantum framework is entirely outside its reach. Whatever lies at and above the Planck scale is not an extension of the Standard Model. It is a replacement of the conceptual foundations on which the Standard Model is built. The Standard Model contains three separate forces, each with its own mathematical structure, its own set of force-carrying particles, and its own coupling strength describing how strongly it acts on the particles it affects. Electromagnetism is described by a symmetry group called U1. The weak nuclear force is described by SU2. The strong nuclear force is described by SU3. Together they form the gauge symmetry of the Standard Model, written as SU3 times SU2 times U1, a product of three independent symmetry structures that happen to coexist in the same framework without any deeper explanation for why these three and not others, why these coupling strengths and not different ones, and why the particle content is organized the way it is across the three forces. The coupling strengths of the three forces are not fixed constants. They change with energy, a phenomenon called running of the coupling constants that follows from the quantum field theory treatment of how forces behave at different scales. At low energies, the strong force is much stronger than electromagnetism, which is much stronger than the weak force. But as energy increases, the strong force weakens, electromagnetism strengthens slightly, and the weak force strengthens. The three coupling constants evolve with energy in ways that can be calculated precisely from the Standard Model, and the natural question is whether they converge to a single value at some high energy scale, suggesting that the three forces are actually different manifestations of a single unified force that appears as three separate forces at the lower energies accessible to experiment. When the running of the coupling constants is calculated using the Standard Model alone, the three curves approach each other at high energies but do not meet at a single point. They come close, tantalizingly close, but the convergence is imperfect. This near unification is suggestive enough to have motivated the development of grand unified theories, extensions of the Standard Model that embed the three gauge symmetries into a single larger symmetry group that breaks down into the Standard Model's three separate symmetries at lower energies. In a grand unified theory, the three forces are genuinely unified at high energies, with the splitting into three separate forces being a consequence of symmetry breaking as the universe cooled from its initial high-energy state. Grand unified theories make specific predictions that go beyond the Standard Model. The most striking is proton decay. In the Standard Model, the proton is stable, protected by conservation laws that prevent it from decaying into lighter particles. In grand unified theories, the unification of quarks and leptons into common multiplets allows processes that violate these conservation laws, permitting the proton to decay into a positron and a neutral pion or other combinations of lighter particles, with a lifetime that depends on the specific grand unified theory, but is in all cases enormously long compared to the age of the universe. Proton decay has been searched for in massive underground detectors for decades. The most sensitive searches using detectors containing tens of thousands of tons of water or other materials and running for years have found no confirmed proton decay events. The non-observation has ruled out the simplest grand unified theories, pushing the predicted proton lifetime beyond what those theories allow. More complex grand unified theories with longer predicted proton lifetimes remain viable but untested, awaiting detectors sensitive enough to probe the relevant lifetime ranges. Grand unification remains a compelling theoretical direction that the near convergence of the coupling constants strongly suggests, but it has not been experimentally confirmed, and its simplest realizations have been experimentally excluded. The hierarchy problem, the fine-tuning of the Higgs mass against enormous quantum corrections, motivated one of the most developed and most searched for extensions of the Standard Model. Supersymmetry proposes that every particle in the Standard Model has a partner particle, called a superpartner, with identical quantum numbers except for spin. Particles with half-integer spin, fermions like quarks and electrons, have superpartners with integer spin, called bosons. Particles with integer spin, bosons like photons and gluons, have superpartners with half-integer spin called fermions. The superpartners are given names by adding a prefix or suffix to their Standard Model counterparts. The superpartner of the electron is the selectron. The superpartner of the quark is the squark. The superpartner of the photon is the photino. The motivation for introducing this doubling of the particle content is precise and mathematical. The quantum corrections to the Higgs mass that create the hierarchy problem come from virtual particle loops, contributions from every particle that couples to the Higgs field. Fermion loops and boson loops contribute with opposite signs to these corrections. In the Standard Model, the contributions from fermions and bosons are unrelated in magnitude and do not cancel. But in a supersymmetric theory, every fermion has a boson superpartner with exactly the same mass and coupling strength, and the contributions from each superpartner pair cancel precisely against each other. The enormous quantum corrections to the Higgs mass that require fine-tuning in the Standard Model are eliminated in a supersymmetric theory, with the cancellation following automatically from the symmetry rather than requiring unexplained parameter adjustment. Supersymmetry also improves the unification of coupling constants. When the running of the coupling constants is calculated in a supersymmetric extension of the Standard Model, rather than in the Standard Model itself, the three curves converge much more precisely to a single point at a high-energy scale. The near unification that the Standard Model produces becomes precise unification in the supersymmetric case, suggesting that supersymmetry is not just a solution to the hierarchy problem, but a necessary ingredient in the grand unification of the forces. Additionally, the lightest supersymmetric particle, if it is stable and neutral, is a natural dark matter candidate, providing a solution to the dark matter problem that emerges automatically from the same framework that addresses the hierarchy problem. These three simultaneous solutions to the hierarchy problem, the unification of forces, and the dark matter problem made supersymmetry the dominant framework for physics beyond the Standard Model for several decades. The expectation was that superpartners would be discovered at the Large Hadron Collider at CERN, which began operating at high energies in 2010. The collider was built with sufficient energy to produce the superpartners that supersymmetry predicted should exist at the electroweak scale if the hierarchy problem was to be naturally resolved. No superpartners have been found. The Large Hadron Collider has searched extensively across the mass ranges, where supersymmetric particles were most naturally expected, and the searches have returned nothing. The absence of superpartners at the expected mass scales does not rule out supersymmetry entirely, since superpartners could exist at higher masses that the collider has not yet fully explored. But it has eliminated the most natural versions of supersymmetry, the versions that most cleanly resolve the hierarchy problem without introducing their own fine-tuning. The framework that offered the most elegant solution to the Standard Model's deepest theoretical problem has not appeared in the one place it was most confidently expected to show up. The hierarchy problem can be approached from a direction entirely different from supersymmetry. Instead of introducing new particles whose quantum corrections cancel the Higgs mass corrections, the approach of extra dimensions asks whether the problem is real in the first place, or whether it is an artifact of assuming that spacetime has only 4 dimensions. If spacetime has additional dimensions beyond the 3 spatial and 1 temporal dimension of ordinary experience, the relationship between the electroweak scale and the Planck scale changes in ways that can dissolve the hierarchy problem rather than solve it. The core idea is that gravity appears weak compared to the other forces because it is diluted across extra dimensions that the other forces do not propagate into. In ordinary 4-dimensional spacetime, the gravitational force between 2 particles falls off with the square of the distance between them, following the inverse square law that Newton identified and general relativity refined. If spacetime has additional compact dimensions that are curled up into small loops rather than extending infinitely, then at distances smaller than the size of those compact dimensions, the gravitational force falls off more steeply, following a higher power of the inverse distance law. At distances larger than the compact dimensions, gravity reverts to the familiar inverse square behavior, but its apparent strength at those large distances is reduced by a factor that depends on the size and number of the extra dimensions. If the extra dimensions are large enough, this dilution factor can account for the enormous apparent weakness of gravity relative to the other forces without requiring the Planck scale to sit at its conventionally assumed enormous value. The true Planck scale, the energy at which gravity becomes strong, could sit much closer to the electroweak scale if the extra dimensions are sufficiently large, making the hierarchy between the 2 scales much smaller or eliminating it entirely. The apparent hierarchy is not a fundamental feature of the physics. It is a geometric artifact of gravity propagating through extra dimensions that the other forces do not access. This framework makes specific predictions that distinguish it from the Standard Model. At the Large Hadron Collider, if extra dimensions exist at the relevant scale, gravitons, the hypothetical force carriers of gravity, could escape into the extra dimensions during high-energy collisions, carrying away energy that would appear as missing energy in the detector. Additionally, the collider could produce microscopic black holes if the true Planck scale is close enough to the electroweak scale, since black holes form when energy is concentrated into a small enough region, and the threshold for that concentration is set by the Planck scale. Neither graviton emission into extra dimensions nor microscopic black holes have been observed at the Large Hadron Collider. The searchers have placed tight constraints on the size of extra dimensions and the scale at which extra-dimensional gravity would become detectable, ruling out the parameter ranges where the simplest extra-dimensional models predicted observable effects. Like supersymmetry, extra dimensions remain theoretically viable in versions that push their signatures beyond current experimental reach, but the most natural and directly testable versions have been constrained significantly. What extra dimensions contribute to this chain beyond their status as an unconfirmed theoretical proposal is a demonstration of how deep the Standard Model's problems run. The hierarchy problem is severe enough that it has motivated not just new particles, but new dimensions of space-time as a potential resolution. The framework's inability to explain the relationship between its fundamental energy scales has driven theoretical physics toward proposals that would require revising the most basic assumptions about the dimensionality of the physical world. That the problem remains unsolved despite decades of theoretical ingenuity and experimental search is a measure of how far the Standard Model sits from a complete description of nature. Every gap identified so far in this chain has been a gap in the Standard Model's description of the physical content of the universe. Missing forces, missing matter, missing energy, unexplained parameters, unresolved hierarchies. Each is a place where the framework's reach ends and something beyond it begins. But there is a gap of a different character, one that sits not at the edge of the Standard Model's domain, but at its foundation, embedded in the quantum mechanical framework that the Standard Model is built on. That gap is the measurement problem, and its presence at the base of the entire theoretical structure means that the Standard Model inherits an unresolved foundational problem that no amount of particle discovery or parameter explanation can fix. The measurement problem was introduced in the context of quantum entanglement earlier in this series. Here it appears again, but from a different angle. The Standard Model is a quantum field theory, meaning its fundamental objects are quantum fields whose states are described by wave functions evolving according to the Schrödinger equation. The wave function of a quantum field carries all the information about the field's state, describing superpositions of possible configurations with associated amplitudes. The evolution of the wave function is deterministic and continuous, governed by the equations of motion of the theory, and it preserves superpositions rather than selecting from them. But the Standard Model also makes predictions about measurement outcomes, and measurement outcomes are definite. When a particle detector fires, it registers one outcome, not a superposition of outcomes. When the Higgs boson was detected at the Large Hadron Collider, each collision event produced a specific set of decay products, recorded by specific detector elements at specific locations and times. The theory predicts probabilities for these outcomes through the Born rule, and those probabilities match the observed frequencies with extraordinary precision. But the theory does not describe how a definite outcome emerges from a quantum superposition, because the Schrödinger equation never produces definite outcomes from superpositions. It evolves superpositions into larger superpositions. This gap between the deterministic evolution of the wave function and the definite outcomes of measurements is the measurement problem, and it has no agreed resolution within quantum mechanics or within the Standard Model built on top of it. The Copenhagen interpretation, the most widely used practical framework, sidesteps the problem by treating measurement as a primitive concept that does not require further analysis, with the wave function collapsing to a definite outcome upon measurement, without specifying what constitutes a measurement or what physically produces the collapse. The many worlds interpretation removes the collapse entirely, but introduces a branching structure whose relationship to observed definite outcomes requires careful justification. Pilot wave theories introduce hidden variables that restore definiteness, but at the cost of explicit non-locality. None of these interpretations is part of the Standard Model. The Standard Model makes no commitment to any of them. It uses the Born rule to extract probabilities from wave functions, and compares those probabilities to observed frequencies, without addressing what happens at the moment of measurement that produces a specific outcome from a quantum superposition. The framework is operationally complete, meaning it produces correct predictions for every experiment that has been performed, but it is foundationally incomplete, resting on a measurement postulate that it cannot justify from within its own mathematical structure. A truly complete theory of physics would not just predict measurement probabilities. It would explain what measurement is, why it produces definite outcomes, and how the classical world of definite objects and events emerges from the quantum world of superpositions and amplitudes. The Standard Model inherits this problem from quantum mechanics and adds nothing toward its resolution. The most precisely tested theory in the history of science is built on a foundation whose interpretation remains unresolved after nearly a century of debate, and that unresolved foundation is not peripheral to the framework, but central to everything it does. The Standard Model contains 19 free parameters. These are numbers that must be measured experimentally and inserted into the framework by hand, because the theory itself provides no mechanism for determining what their values should be. They include the masses of the 6 quarks and 3 charged leptons, the coupling strengths of the 3 forces, the parameters describing the mixing between quark generations, and the parameters associated with the Higgs field, including its mass and the strength of its self-interaction. Each parameter has been measured with varying degrees of precision, and together they define the specific version of the Standard Model that describes the universe we inhabit. The existence of free parameters in a physical theory is not unusual. Every theory has some inputs that must be determined from experiment rather than derived from first principles. The problem with the Standard Model's 19 parameters is not their existence, but their character. They span an enormous range of values with no apparent pattern or organizing principle. The top quark mass is roughly 300,000 times larger than the electron mass. The strong force coupling is roughly 30 times larger than the electromagnetic coupling at the electroweak scale. The mixing angles between quark generations take specific values that fit no obvious geometric or algebraic pattern. The parameters are what they are, and the framework that contains them offers no insight into why they are that, rather than something else. A complete theory would explain these values. It would either derive them from deeper principles, showing that they are the unique values consistent with some more fundamental symmetry or constraint, or it would show that they are environmental variables whose values differ across different regions of a larger multiverse, with the observed values being those consistent with the existence of observers. Neither explanation is available within the Standard Model. The parameters are inputs, not outputs, and the framework is silent on their origin. The particle content of the Standard Model raises the same question from a different angle. There are 3 generations of matter particles, each a heavier copy of the one below it, with no other difference in its interactions or quantum numbers. The electron, muon, and tau are identical in every property except mass. The 3 generations of quarks mirror this structure. Why 3 generations and not 2 or 4 or 17? The Standard Model accommodates 3 generations but does not explain them. The number 3 is an input to the framework, not a consequence of it, and no known principle selects 3 as the unique correct number of generations. The gauge symmetry of the Standard Model, the SU 3 times SU, 2 times U, one structure that defines the 3 forces and their associated particles, is similarly unexplained. Why these 3 symmetry groups? Why not a different combination? Why does the strong force have 3 color charges while the weak force has 2 isospin states? The Standard Model is built on these symmetries, but does not derive them from anything deeper. They are the symmetries of the world as measured, incorporated into the framework, because they work, with no explanation for why the universe chose them over the infinitely many alternatives that could in principle have been realized. Each unexplained parameter, each unexplained symmetry, and each unexplained generation is a question mark that a complete theory of physics would resolve. Together, they paint a picture of a framework that is extraordinarily successful as a description of observed phenomena, but completely silent on the question of why the phenomena are the way they are. The Standard Model describes the universe with precision. It does not explain it, and the gap between description and explanation is where the deeper theory must eventually be found. The chain has mapped 16 layers of incompleteness in the most successful scientific theory ever constructed. Gravity excluded from the quantum framework. Dark matter composing 27% of the universe's energy, with no Standard Model particle to account for it. Dark energy composing 68%, with a theoretical prediction wrong by up to 120 orders of magnitude. Matter dominating over antimatter through a CP violation mechanism too weak by many orders of magnitude. Neutrinos carrying mass that the original framework cannot accommodate. The Higgs mass requiring cancellations of 34 decimal places with no stabilizing mechanism. Parameters fine-tuned to values the theory cannot explain. The strong force respecting CP symmetry to a precision the theory does not guarantee. Quantum gravity inaccessible to the framework at any energy. Grand unification suggested but unconfirmed. Supersymmetry